Find the rate at which the diameter decreases when the diameter is 10 centimeters. We've got a snowball. I'm going to draw you a picture of a general snowball. We don't see these in Texas. We're assuming it's spherical, okay? And since it's a sphere, it has a radius. And what's happening is as it melts, it gets smaller. So obviously if it gets smaller, that means the radius is decreasing. But as it gets smaller, the surface area decreases also, and the volume. All those things are getting smaller. But in this particular problem, they're interested in finding the rate at which the diameter decreases. So I'm going to start writing that stuff down. I want to know the rate at which the diameter decreases. So I want to know the rate at which the diameter decreases. I want to know capital D is diameter. I want to know that rate. I know it's going to get smaller, but what is the rate it does? I want to know that at exactly the moment when the diameter is 10 centimeters. And what I'm given in the problem, and I could draw my instant in time now, because at the instant in time, I know that this snowball has a diameter all the way across of 10 centimeters. That's the instant in time. But I'm given that just the way it melts, its surface area is decreasing at a rate of 1 square centimeter per minute. So the rate at which its surface area, I'm just going to put A, and not surface area, just area, and we understand it means surface area. The rate at which it's decreasing is 1 centimeter squared per minute. Now it's decreasing, so since it's decreasing, I'm going to put -1 centimeter squared per minute. Right, so let's just recap. We've got a snowball, right? We've got this snowball. It's melting, so it's getting smaller. It's getting smaller in a way that the area decreases at 1 centimeter squared per minute. I want to know at the exact moment that the diameter of the snowball is 10 centimeters, how fast is the diameter shrinking? So I need a way now to relate the diameter of a sphere, a ball, to the surface area of the ball. So we're going to have to look this formula up. The formula should be, I think it's on your first page of your formula sheets. Yes, it is. Has a sphere there. It says V is 4/3 pi r cubed, and then right below it you'll see it says A is equal to 4 pi r squared. So we know that the area of a sphere is 4 pi r squared. Now this is good. That's a good formula because it has area in it, but it doesn't have diameter. It has radius. So there's a couple of things we can do here. We can just work with that, or we can actually try and replace that r with d. And just remember that when it comes to the relationship between r and d, the diameter is twice the radius, right? So if I solve this for r, I get half the diameter is the radius. So I think that's obvious to most of us. I could take this and just go into this formula and replace that r with 1/2 d before I take a derivative. But be careful, it's being squared, so I'm going to put 1/2 d squared. And the importance of putting in parentheses is that you have to square the half. So you square 1/2, you get 1/4. You can bring that out, and it cancels out with that 4. 4 times a fourth is 1. So you're still going to have just pi here, but now the constants are kind of gone except for pi, and then you have capital D squared. And that's actually a pretty nice formula. I can differentiate that with respect to time now. So dA dt equals, the pi is going to stay, the 2 is going to pop out, so 2 pi d to the first power times chain rule, the derivative of d, capital D with respect to time, and dA dt I'm given, capital D I'm given, 10, and dd dt is what I want. So I have everything I need here. So let's rewrite it. Left side becomes -1. equals 2 pi times capital D, which was 10, and then times dd dt. This is negative 1 equals, I'll just multiply those together, 20 pi dd dt, and then divide through by 20 pi. So I have it, negative 1 over 20 pi. That's a very small number. Now, what is the unit there? Well, d is the diameter, right? And the diameter of the sphere should be measured in centimeters because everything's in centimeters. So the units on this should be centimeters diameter over the unit of time, which is minutes, centimeters per minute. So as this snowball melts, the area is decreasing, the surface area is decreasing at negative 1 centimeter squared per minute. At the moment the snowball is 10 centimeters in diameter, the diameter is actually shrinking at a rate of negative 1 over 20 pi centimeters per minute. Awesome. 12. I think this will be my last one for right now. I always tell you all that, but it really doesn't matter to you, right? All right, this one's going to be tricky. This one's different. It's very strange. At noon, okay, at noon, I'm just going to start writing things down. At noon, ship A is 150 kilometers west of ship B. I'm going to just put B. Ship A is, okay, let me just draw this situation right here. West, so if we were to put a map here, okay, north, east, south, west, right? Then I can just start putting my ships here. And I don't even think I'm going to use the map. I'm just going to put at noon, here's what I've got. At noon, you've got ship A right here. You've got ship B right here. And the distance, it's A is west of B, so west is that direction, so this is 150 kilometers. Okay. That's the start. All right, next thing. Ship A is sailing east at 35 kilometers per hour. So this ship right here, A, is sailing east. It's going in that direction at a rate, so that's a derivative, at a rate of 35 kilometers per hour. So I'm just going to put that above here. 35 kilometers per hour. I hope that comes out on camera. Ship B is sailing north at 25 kilometers per hour. So this ship is sailing north at 25 kilometers per hour. Okay, so they're sailing at exactly noon. This one's 150 kilometers west of this. A is west of B, but A is moving this way and B is moving that way. How fast is the distance between the ships changing at 4 p.m.? All right, so let's look at what's happening at 4 p.m. That's my picture at noon. See, this is a problem where I don't really have the general picture, instant picture. It's not coming right away because it's not as a simple geometric shape, all right? It might turn into one, but just right now I'm just writing down the information, trying to make sense out of the picture, or out of the words. So let's see, at 4 p.m., that's 4 hours later, right? That's 4 hours later. What's happened is that this ship here, A, has moved how far in 4 hours? So you take this number, this is kilometers per hour, in 4 hours it will have moved 140 kilometers. So you just take that, multiply it times 4, it's 140 kilometers. Let me draw, this is where they were to start, okay? So this ship A has now sailed to here, right? It's now gone 140 kilometers. which means it's still 10 kilometers from where B started. Fix that. So A is right there now. And then B has sailed for 4 hours at 25 kilometers per hour. It's now 100 kilometers away. So B has gone up here and now is 100 kilometers away. This length right here is 100 kilometers. And that's where B is now. Okay? If that makes sense. This, if I say this was the starting point of B and this was the starting point of A, that's this point and that's this point. So in 4 hours, A has gone from here to here, and B has gone from here to here. It's saying at that instant, right now, at 4 p.m., find the rate, sorry, I looked at the wrong problem. How fast is the distance between the ships changing? So they want to know at that exact moment in time, how fast is that distance right there between them changing? So this one's still coming in, this one's still going up, and that purple line is changing as they move. So this is the initial situation. This is a situation at the instant in time, so I think I will label this instant. And now what I need to try and do is come up with some sort of general picture. So this is what happened after 4 hours, but what would have happened after 1 hour or 2 hours, or maybe just like H hours? How about that? At H hours, what would it have looked like? Well, we can make this a lot more complicated than it has to be, all right? What I want you to see is this picture. I'm going to erase this for right now. What I want you to see is that we have a right triangle, okay? And here's the situation. We have this base, and we have this side, and we have this hypotenuse. It's a right triangle because it was east-west, north-south. And I know that this side right here represents the length of the distance from ship A to this point. And I know that that side, I can call it anything I want. I'm going to just call this X. And I know this side right here, I can call Y. All right, great. And then let's call this right here Z, the hypotenuse. Let's call it Z. We could have called it H for hypotenuse, but all right, there we go. That's the distance, these distances. Now, what I'm given in the problem is that X is changing. And I'm given the rate at which this is shrinking, because when we start out, we're here, so X is this whole length, and then X starts to shrink, 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 shrink. So the rate at which it shrinks is the speed of the ship. And the speed of the ship A is 35 kilometers per hour. So I know that this shrinks at a rate of 35 kilometers per hour. If it were going the other direction, going away, then it would be positive. Now dy dt, dy, this was dx dt, not dx dy. I don't know why I put that. Dx dt, the rate at which x changes with respect to time is this. The rate at which y changes with respect to time is actually going to be positive, because as ship B sails, it goes this way, y gets bigger. So I use a positive number here, and it was 25 kilometers per hour. And what I want to know is the rate at which z is changing with respect to time. And when do I want to know that? I want to know that when this ship is here and this ship is here. So in terms of my triangle, this side right here is x, right? And at the moment in time, 4 p.m., that's 10, right? That's 10. So I want to know this at the moment that x is equal to 10 kilometers. See, I can't say 140, because 140 kilometers is how far it's sailed. When I get to 4 p.m., this side of the triangle is 10 kilometers. So that's why I'm using 10. And then for the y value, it's this distance, which is the 100 kilometers. So when y equals 100 kilometers. I really hope that makes sense. All right. I just need now an equation that is going to relate x, y, and z together. And that's a right triangle. We have the Pythagorean identity, a squared plus b squared is c squared. So I can write x squared plus y squared equals z squared. None of these are constant, right? As the ships move, none of those stay the same the whole time. At the instant, at 4 p.m., yes, we can talk about what they are, but not yet. We have to take derivative first. So we take derivative with respect to time of each of these. And they're all going to look very similar. We have to do chain rule. So 2x and then the derivative of x with respect to t, plus 2y and then derivative of y with respect to t, equals 2z and then dz dt. So all those derivatives, we use the chain rule. Do I know what x is at the moment in time? Yes, it's 10. Do I know what dx dt is? Yes. Do I know what y is? Yes. Do I know what dy dt is? Yes. Do I know what z is? No, I don't, actually. Dz dt is what I want. So the only thing I really just need to resolve is this z. Do I know what it is? Well, I can fix the moment in time right now. If I fix the moment in time, my triangle looks like this, 10, 100, and so this side I can get z, right? Because I can just use Pythagorean. So I know 10 squared plus 100 squared must equal z squared. So 100 plus 10,000 equals z squared. So 10,100 equals z squared. And I'll take the square root on my phone. (10,100) square root 100. So z is equal to, I'll put it here, z is equal to 100.498. Really close to 100. So now I just plug in. Also notice there's a 2 here, 2 here, 2 here. I could divide both sides by 2. That'll just make my computation a little bit easier. This is gone, that's gone, that's gone. And so I have 10 times 10 is x, dx dt is negative 35, plus y, which is 100, times dy dt, which is 25, equals z, which is 100.498, and then dz dt. So let me compute this. So we have negative 350. I didn't need my calculator for that. Plus 2,500 equals 100.498 times dz dt. And I put those two together and divide by this. 498 equals 21, you get a positive number, 21.39 equals dz dt. And this is measured, the units here, z is the measurement from here to here, and we're measuring lengths with kilometers. So this is 21, I'm going to say 0.4 kilometers per, and then time unit here was hours. That's the rate at which the ships are moving relative to each other, right? The distance between them is actually increasing at a rate of 21 kilometers per hour. I'm going to check this real quick. This is number 12. Let's see if I even have even numbers answers in here. I don't think I do. I'll check it, and if it's wrong, I'll put a note, but pretty sure all the math there is good. All right, continue in a little bit. Okay, I'm going to continue working the problems here for 2-7. I finished up with number 12, and so I'm going to start here with number 13.